Welcome to this lecture on material selection in mechanical design. My name is Nas Ghonim, and I'm a professor at UCLA. I'll be talking today about the idea of material selection and some of the key properties that we would use in dealing with high temperature components. So I will kind of review what is known about in very short order, the ranges of materials, the types of materials we could select from, their main characteristics, and then I'll rely on some data from the literature to tell you something about their properties, the key properties in terms of strength and ductility and temperature capabilities. And then we will kind of finish this section working with the so-called Ashby charts, which I think some of you have seen already in my earlier design lectures last year, but we're going to be specific this time on the key properties that allow us to do a good thermomechanical design. So let's look here at the idea of high temperature components, and we will see that the materials for high temperature applications, we need to kind of measure their importance as in dealing with high heat flux. So this chart shows you a figure of merit, and the figure of merit is shown as kilowatt hour. You know, the kilowatt hour is a unit of energy we have in our electric consumption. For example, an average house consumes about 20 to 30 kilowatt hour per day for the whole house in electric. So if this energy is passing through 1 centimeter square of the material, and the material will fail beyond that point, that could give us a relative figure of merit. For example, if we have 100 kilowatt hour per centimeter square, that could be like an expression for the lifetime of the material, versus a material that can last for 1,000 kilowatt hour per centimeter square. This has a much higher capability. So the capability or the survival of the material can be measured in terms of energy per unit energy flux. And that energy flux is expressed as a function of the heat flux impinging instantaneously on the material. So heat flux is in megawatt per meter square. So roughly around maybe 0.1 or 0.2 megawatt per meter square, we can have materials that can be cooled passively through convection or radiation. For example, solar panels, iron grids in space propulsion can be that. But something like a Hall thruster, which is for space propulsion also, falls in between, and therefore some designs can be cooled, or if the Hall thruster power is high, then it has to be cooled actively, or if it is low, then it can be cooled passively. Now, if you go to turbine blades in jet engines, then the heat flux is relatively high. That's 1 megawatt per meter square approximately on the blades themselves, and therefore they last only a short period of time or short duration of several hundred kilowatt per centimeter square, and so forth. So all of this indicates that future developments will put higher demand on materials in terms of their heat flux capabilities. We might expect some materials to handle heat fluxes of up to 100 megawatt per meter square, but not in a steady state or continuous fashion, but more likely in a pulse or intermittent fashion. And the lifetime would be improved. So that kind of the future development of materials here. Now, another way to look at it is measure, this is from Ultramets, which is a company here in California for high temperature materials, showing the heat flux in watts per centimeter square this time versus the temperature capability approximately of certain materials. So if you have heat flux of 100 watts per centimeter square, that's equivalent to 0.1 megawatt per meter square, then that is typically for rocket nozzle throat, internals, combustion engine, and so forth. And the temperatures expected for these materials will be on the order of 3000 Kelvin. For re-entry vehicles, the heat flux is much higher, 10 megawatt per meter square or 1000 watts per centimeter square. And the temperatures could be extremely high. If this case, if not cooled, then we have to use charring and evaporation methods of the material to sacrifice the material itself. A third way to look at the temperature capabilities of materials is shown here from the work of Mitham in Journal of Material Science. And it shows the different technologies and the corresponding material capabilities. For example, Mach 2 airframes, you can use aluminum. This is a melting point of aluminum alloys here. So you use aluminum. Steam generation, then the maximum temperature limit is right here, maybe 600-700 degrees centigrade, and that's kind of a fraction of the melting point of nickel and iron types of materials. So alloys that are based on nickel and iron would be useful. For jet engines, you need higher temperatures, and therefore you would need to do a lot of work, because you see the temperatures here, one has to use a good fraction of the nickel melting point, for example, to achieve these conditions for jet engines. Petrochemical processing, we need even higher temperatures, up to 1500 degrees C. Apollo spacecraft re-entry, you go up to 2000. Material processing, you need even higher temperatures, up to over 2000 degrees centigrade. And an example of even the electric light filament itself, the tungsten filament can work close to 2600 degrees C. So that's a kind of a high temperature component, even though it's very simple, but its design is like a miracle that it can work for such a long time, burning at such high temperatures and radiated cooled. Rocket nozzles would have temperatures close to 3000, the combustion zone, and the hypersonic space vehicle re-entries are way above that maximum limit, and therefore we have to use ablation of plastics to achieve these temperatures. And that gives you kind of the materials that we use. You got nickel, iron, titanium clustered here, melting point. You got silicon carbide and aluminum oxide, and all of the oxides are here. You got the refractory metals, tungsten, and then finally you get something like a hafnium carbide up here that has a very high temperature capability. So if we look now at a rough classification, the first consideration we have is the melting point. So if we take the melting point and we stress the material, then roughly we would say we're going to use it at 1/3 of its melting point. If the material is not stressed, then we have to kind of back down. So the idea for material selection is that if the utilization is going to be in a high pressure region or a region that has high thermal stresses, producing large stress on the component, then we cannot use it more than maybe 30%, 40% of the melting point, as I'll show you in the properties. But in certain situations, the stress on the material is by design is not very high, but we just need it to survive the high temperature, for example, in the re-entry vehicle case. So in that case, we can actually exceed this rule of thumb, and we can go all the way up to maybe 75% of the melting point if we guarantee that the stress is low. So these are considerations that will come out of your design after you do the analysis in the project. So going back here, a look on the chart on the right. These are the melting points of the highest melting points known on Earth. It is hafnium carbide, 3890 degrees centigrade. And tantalum carbide is just a smidge below, 3880. And then you can rank now groups of materials that have higher melting points. The carbides, hafnium, tantalum, zirconium, these are the top three. And then you got the tungsten, 3410, very high melting point metal. So this is a metal, it's not a ceramic. These three are ceramic materials. And then you start alternating between metals. We call them refractory metals like tungsten, rhenium, tantalum, and then molybdenum. So these are the refractory metals. And then in between you find carbides, titanium carbides, niobium carbides, and tantalum, and then nitrides come in. So you have borides, carbides, and nitrides as the top ceramic materials of the refractories. So you can have tantalum, zirconium, boron, or the refractory metals themselves will be a group. And then in addition to this, we have the silicon carbides, 2700 degrees C, and then you get some of the materials that are used for coatings, like iridium, for example, 2400. Boron is a very light metal, and it has a very high melting point, 2300. And that's why when you combine it with carbon, you get very tough, high ceramic boron. Nitride, for example, is used in the hole thrusters as an insulating material. And then in the bottom here, you just start seeing iron at 1535, and nickel is 100 degrees below, and copper is a few hundred degrees down. So the copper is almost like 1/3 of the melting point of tungsten, and it's used in lower temperature applications. So these are all the materials, and therefore I'm going to classify them in a roughly high temperature materials, HTM, from 300 to 750, and you find alloys of iron, nickel, cobalt, titanium, and vanadium. Titanium is a hexagonal close-packed crystal structure. Vanadium is body center cubic. Cobalt is BCC. Nickel is face center cubic. Iron is body center cubic. Ultra-high temperature materials are those for use in the 750 to 1500 degrees C, and this is some the refractories like molybdenum, rhenium, tantalum, and tungsten, in addition to the silicon carbide and carbon-carbon composites. And then extreme high temperatures, those are above 1500, and these are mainly the carbides and the borides and the nitrides of hafnium, tantalum, and zirconium. So once we have that, then we can look now at specific properties for high temperature applications and typical operating temperatures. So in this chart, we see the relative density corrected strength. So this is the strength divided by the density. So if we are selecting material and the material has the strength, and the material itself has high strength, but we need it in a rocket engine, for example, where the weight is an important factor, we would like to have it as light as possible. So the strength divided by the weight is sometimes an important design constraint that we have to have. And in this case, you'll find that some materials like carbon-carbon composites or silicon carbide composites become important parts of that mix of materials that we would use. So I will show now the range of temperatures that is for use in different materials according to this study that we have from Mech. So if you find aluminum, the maximum temperature is 300 degrees centigrade, TU, T ultimate over T melting. This is approximately 45% of the melting point. The low alloy steel is 580, as we've seen in the first wall design of the fusion reactor that I presented earlier in the last lecture. And the oscillating steels can work up to 600 degrees C. But then once we get into jet engines, the blades must be made from nickel-based super alloys, and that can work up to 1,000 degrees centigrade with a lot of engineering, material science, so that we can use this alloy up to 77% of the melting point. Very unusual under stress conditions. If the conditions are very low stress, then we could use nickel, alumina, tungsten up to very high temperatures and a significant fraction of the melting point. Next, we look at the actual strength of the material, and the strength could be an ultimate strength of the material as a function of the operating temperature. And generally, again, you find that aluminum works at low temperatures to 300, and the strength is ranges 200 to 400 megapascal. And then above the aluminum, you get titanium alloys. These are light metals used in some aircraft. Stealth aircraft, for example, the skin of stealth aircraft is made of titanium because it's very strong and light, but the upper temperature capability is still limited to, as the temperature increases, then you notice the strength decreases in general. Steels are higher than the titanium, but still limited to 500 or 550 degrees centigrade if we sacrifice some of the strength of the steel. And then we move on to from steels to nickel-based super alloys, and that's a whole large group of alloys, the strongest of which can work at lower temperatures. The highest temperature would be reserved for alloys that have relatively lower strength. So those that can operate at 1,000 degrees centigrade would have to be designed to handle lower strength levels. And then you get a group of nitrides and carbides, the silicon carbide and silicon nitride. These are ceramics and up to 1,500. And then you get the refractory metals. They have lower strength, but they can handle up to 2,000 degrees centigrade. The exception here is the carbon-carbon composite, which is made from layup, 090 layup, and those can have relatively stable strength up to way above 2,000. Only problem with those is oxidation, so we have to coat them, or in aggressive environments, we have to be careful how they are utilized. Now I'm going to go through the properties of each one of these alloy systems to be familiar with the levels of strength and some of the key properties like for example, creep rupture properties of these high temperature alloys that we will be considering in our material selection early on in the design phase of the project. So looking first at these properties, I would suggest that you look at a useful source of materials data. It's called MathWeb, and you can have a free subscription to MathWeb, and with the free subscription, here is the link. You can obtain many of the material properties that you might be able to use in your project. Here's, for example, the aluminum alloys 2024, 7077. These are all alloy systems that have been developed over the years, and it shows that these are high strength but low temperature. As you go to higher temperature alloys, then the strength level decreases. So it's a sacrifice, it's a combination. Do you need high strength and low temperature, or do you want to go with high temperature and low strength? and that is the choice that we will have to make for all of the materials, in fact. So next, we will have to consider now steels, and steels are used in power plants, and these are called alloy steels. Alloy steels that must have chromium for oxidation protection, molybdenum, vanadium, and tungsten. Those are they form carbides, and the carbides stabilize the steels at very high temperatures. So this chart shows you the creep rupture in 1,000 hours. So if I put the material under creep conditions and I wait for 1,000 hours, then the question is that what is the strength that will make it rupture? So that's a measure for high temperature performance. So the creep rupture in 1,000 hours is one measure. Of course, you can measure it in 100 hours or 10,000 hours, but relative ranking will be not disturbed. So 1,000 hour ranking gives you the stress that the material can take, 100 to 200 to 300 MPa, and the temperature between, let's say, 500 all the way to 700. So this is the range of all steels possible. It's alloy steels that are used in the power generation industry, like in tubings, pressure vessels, and the like. Next is the titanium alloys, as I mentioned, for some of the aircraft components, and because it's very light, and if you have high speed, then the skin has to take some temperature. So you have a titanium 6-4, for example, here. The capability is up to 400 degrees C. There are other titanium alloys, IMI alloys, that can go up to 500, 550. And again, the range is very similar to steels, from 100 to 500 MPa. So you can see 100, 300, 200, 600. So that's kind of the range that you'll be considering in most of the designs, and will be allowed to use that one. Now I will switch next to the next class of alloy systems, and these are the alloy systems for that have very interesting capabilities. It has been, well, even though the nickel melts at temperature less than the steel, than the iron. For instance, iron is 1500 C, and the nickel will be 100 degrees lower. But the nickel itself is a phase-center cubic material. It has good ductility, therefore. And therefore, we found, or people found over the years, that alloying nickel can lead to components that operate at higher and higher temperatures. Not only that, but the nickel is resistant to corrosion, so it's very good for using in hostile environments. So that led to the development of nickel-based superalloys. Superalloys means that they are evolution from the earlier versions of nickel-based alloys that have capabilities of 500, 600 degrees centigrade. So the superalloys are a success story where material science and engineering came together to make possible the development of these superalloys that are used in jet engines and critical components of jet engines. So I'll review what happened in the nickel story so we could essentially use it in our designs. So for nickel, we have the table, the periodic table, and by trial and error and some thermodynamics and engineering, there are a number of things happening. If you look at additions of chromium and aluminum, chromium and aluminum form native oxide layer, so they will segregate to the surface and they protect the nickel-based alloy from surface oxidation. Now, if we make nickel into a polycrystal, then we want to make the crystal, the grain size to be stable, so it doesn't enlarge over time, it doesn't become weaker, and therefore we use some elements to pin down the grain boundary. So grain boundary phases can be borides or carbides that will stabilize and pin down the grain boundaries. Now, to make the nickel stronger, we have two things. We have to do precipitation, hardening, or solid solution strengthening. So solid solution strengthening, we use tungsten, tantalum in the matrix to make it stronger. And the precipitation, we can induce it by titanium and by aluminum and also by tantalum. So you have both types of approaches that can lead to strengthening. So you can see now that this kind of engineering is very complicated, and it took a long time to figure out how to increase the upper temperature of nickel-based superalloys as time goes on. So this is for a period of 40 years, from 1940 to 1980. The nickel-based alloys improved from a high temperature to almost super high temperature or ultra high temperature in here over that 40 years. The capabilities improved up to close to 1,000 degrees. So this shows you the 1,000 hour creep rupture under a stress of 150 megapascal. And then you rank all of these materials for these conditions, 150 MPa and 1,000 hours, and then you see how long, what is the maximum temperature at which the material would last. So you see here that we have names that are familiar: Waspaloy, Mnemonic, alloys, Inconel, and then you get the conventional casting, and then the technology that was discovered in the 80s called the directionally solidified and single crystals, and that led to higher creep strength and so on. So that's kind of an important consideration for us when we do the design. Now, in some applications, we have to consider also insulating materials, and you can see the capabilities of insulating materials from 1,000 degrees centigrade to 3,000 degrees centigrade, going from the silicon oxide, aluminum oxide. Silicon oxide, by the way, is kind of a little bit fluid at these temperatures. It has viscosity, and so it's very useful. It's a glassy phase. And then you got the oxide ceramics, zirconia, and alumina. These are very important insulators. And then for high insulation capability, we use fibrous insulations and foams and graphites at these higher temperatures. Now, we talked about the nickel-based superalloys and the fact that they are used extensively as the key material for turbine engine components, especially the turbine blades for the stator and the rotor. There is a tremendous amount of effort now in the engine business, as we know that some of the engine manufacturers are Pratt & Whitney and General Electric in the US and Rolls-Royce in Europe, and there's other companies, of course, but these are kind of the main players in the jet engine business. The idea is that there are certain components in the combustors, for example, the exhaust, that the temperatures need to be very high. And if we can reduce the cooling that is required for these components, you've seen the cooling lines going all over the place. If we can eliminate some of that, then the weight of the engine will drop, because we don't require to push the coolant and its components around. And if the engine weight is going to be reduced, that will be a great benefit, because you will burn less fuel and you can achieve higher efficiency because of the high temperature, and you have less pollution because you can control the chemistry. So because of all of these reasons, there's a tremendous push for the development of carbon-carbon composites and ceramic matrix composites in general in the business. So you can see here that these are kind of going over why do we need ceramic matrix composite. Because we know ceramics are not so tolerant to high stress. They fracture easily, but if we make them into composite form, then we can kind of contain the fracture capabilities, and we will improve engine efficiency in that way. So if there is no cooling or provide significant efficiency boost to the conversion cycle, and the CMCs are much less weight than nickel-based super alloys, and therefore there's a big rush now to develop engines of the future based on CMCs. Now, I'm gonna just discuss, throw in a few ideas about the different materials before we close this chapter or the lecture, and discuss what they mean. So if you look here, these are examples of refractory metal applications. The tungsten has a melting point of 3407, and it's used in high temperature crystal growth crucibles, explosively formed warheads, high temperature furnace elements, and heat shields. Rhenium is ductile. By the way, tungsten doesn't suffer from hydrogen embrittlement, which is a problem for some of the refractories. Rhenium has high ductility, and the strength is very high, and this doesn't have hydrogen embrittlement as well, and it's used in rocket engines, and it's used as also alloying agent for turbine blades. Tantalum has biocompatibility and excellent corrosion resistance, so we use it for coatings and for chemical implants and so forth, high temperature furnaces. Molybdenum, although is 1000 degrees lower than tungsten, but it's more malleable, it's ductile, and therefore it's can use for applications like melt electrodes, and also in thrusters of space applications. Niobium is also a ductile metal, and it's lower cost. Then, in addition to the refractory metals, there are some specialty metals in the platinum group, and these are here ruthenium, osmium, rhodium, iridium, palladium, platinum. All of these groups are related to one another, and they have very interesting and unique property. The palladium group is interesting because palladium has high chemical catalyst ability, so it wants to work with the gases and then to enhance the gas exchange forms and the reactions on the surface. Same thing for iridium and so forth. But although it enhances the catalyst, but it itself does not oxidize. So that makes it ideal for catalytic converters, for example, or it can be ideal for coatings in rocket engines from the inside, because the high combustion process produces high temperature oxidizing environment that can eat out anything that is in its place, and therefore we use this for that purpose as a coating. So they are interesting groups of metals. Now let's talk about the future. So the future is something that we all look for as we develop into design engineers and scientists, and we look at what's going to happen. And I mentioned that the future is going to be going onto the area of micro-engineered materials. And micro-engineered materials and materials that are made not by combination of elements like the old style metallurgy, but actually combination of form. So you change the form of the material, the structure, and the layers and combinations to achieve functions that do not exist in any one particular material or form together. An example, of course, is CMCs, the ceramic matrix composites, because you can weave them and you can infiltrate them with a matrix, and you can adjust the interface conditions between the fibers and the matrix so they can hold it together, and so forth. So this is one example. I'm going to present a couple of examples of micro-engineered materials in advanced technologies. This example here is example for space shuttle orbiter vehicles and thermal ablative materials. So in this case, we need to develop a material that protects the structure and doesn't lead to a disaster. And in this material, we have some fibrous layer, and the fibrous layer can interact with the gas boundary layer and producing char, and the char can leave the material like here, and as it leaves the material, then it carries away the heat, and therefore you don't need to cool it. So there's no cooling for that particular application, but the idea is ablation. So ablation is the response of material to be removed by breaking the bonds and by actually leaving the surface. So you have a sacrificial. And the way works is that you have a three-dimensional weaving and impregnation. So this is an example here where you have, let's say, boride, carbide, nitride of hafnium, tantalum, and zirconium. So these are very high temperature capabilities, but if you kind of make them into a porous structure, then they can be very good and effective thermal shield that can work up to 4,000 degrees centigrade. Another material that we are developing in my laboratory, so the lab is called the Matrix, and the Matrix of materials in extreme environments. This is the lab that I put together for research, and it has a number of PhD students and postdoctors, and the lab is funded by the Air Force Office of Scientific Research and by the Department of Energy and the National Science Foundation. So the idea is that we're developing special materials that can deal with high heat flux and also at the same time plasma erosion. So these materials are shown here, and these have microarchitectures that look very interesting. Pillars or pod-shaped or cauliflower shaped. These are materials that are flexible to expand. This is tungsten, for example, that has different shape, tungsten and rhenium. And they are used to be developed for ion thrusters. This is an ion thruster here, and this is a rendering of the ion thruster where you have the magnets and the propeller, and then the electron are moving this way, and then the ions are coming. This is ion coming, thrusting this way, going through the grid. So in these applications, you have a grid. This is the grid here that's going to be hit by these ions, and we have an anode and a cathode, and the plasma flows between the anode and cathode. These are very high currents, electric currents, and therefore these materials will be under extreme conditions of electricity, magnetics, and heat flux that would be detrimental to their survival. The final consideration that I want to refer to is corrosion, because corrosion is a process that must exist for high temperature materials. And the reason is very simple, because if we rely on cooling to remove the heat, then we have to cool with a fluid. And if we cool with a fluid, we have either a gas, and the gas can be active gas. It can be air, for example. Even air will have also some reactions with the surface. Or it can be a gas that's not active, like helium or argon. These are really expensive gases to use, but helium can be used. Or it can be combustion products themselves, like in the jet engine, which is chemically active. So it can be a gas, or it can be a liquid, and the liquid would be water, for instance, or a liquid metal for some applications, where the liquid metal could be lead or lithium lead or sodium. All of these are liquid metals that have very high heat transfer capabilities because they have mass, and the mass can be used to store the heat and transport it. So under all of these conditions, corrosion is an important consideration, and your selection of material for corrosion must consider those. And you can see here that this is a chart from Dr. Elliott in his article on Corrosion 2000, and it shows the different types of corrosion mode, oxidation, for example, what type of basic alloy type you use. Here is nickel iron, nickel, cobalt. So that's kind of a combination. These are the candidates: 304 stainless steel, 321 stainless steel, and so forth. So this is, the most common here for power industry. Sulfidation for sulfur. You need iron with high chrome. If you have an oxidizing gas, you can also use iron with chrome. Carburization, if you have high carbon environment, then use high nickel alloys with chromium silicon. Nitridation, we have nitrogen environment, you avoid high chromium levels. So he has all of this from experience that would be useful to consider. As you can see, the corrosion can lead to extreme degradation of the properties of the material. And he goes on to halogen effects, fuel ash, molten salts, for instance. Only materials that can be used are nickel-based alloys or tungsten or molybdenum. Some refractory alloys can be used as well as the nickel-based alloys. Liquid metals, you can use iron, and you can use also some of the tungsten and metal alloys that are refractory in nature. So all in all, I think we have now an idea about the different types of materials for high temperature applications, how they're used, and we also have seen that we have to consider a variety of constraints. If you have high stress, you cannot go to high temperature. You might have to lower the stress level to go to higher temperature. So you have a kind of a trade-off between strength and temperature. You have to consider corrosion in your evaluations, because the corrosion can actually remove some of the material from the surface. And you have to consider whether you have your design based on active cooling or passive cooling. So in the next lecture, we will get into Ashby charts of material selection in detail, as we will see next. So with that, we're going to actually stop.